This video is on the objective use even and odd identities in simplifying trigonometric expressions. Now this is the second video, number 2 there, on this objective. So if you've watched number 1 already, I'm going to take a little less time on this one. We're going to take a look at an expression we're given and using very basic, even odd identities, quotient identities, stuff like that. We're going to simplify the expression we're given. All right. So again, if you're unfamiliar with the topic, please click on More Instruction. See the notes or the videos or examples they're giving you, and hopefully that helps. All right, but I'm just going to go into it. All right, so consider only the values of alpha for which the expression is defined. Right? You don't want anything to be undefined. Which of the following is equivalent to the expression below? All right, so I'm going to write this out on paper and go through one method, just one way of simplifying this. Because there are so many of these basic identities, there are typically going to be multiple ways you can simplify a particular expression. So I'm going to show you my way, and then we'll take a look at what they did in their answer explanation, and it's probably going to be something different. We'll see. All right. So before I get into the expression, though, I want to talk about all the basic identities again. I'm going to bring these up in every video for this section. So the one that this particular objective is on are these even-odd identities. Remember the cosine function and the secant function. Those are the only two even functions. So the cosine of a negative angle is equal to the cosine of the opposite angle, and the same for the secant. All right, so the cosine and secant are the only even functions. Have y-axis symmetry when you look at their graphs. Odd functions have origin symmetry, and the other four were odd. The sine of a negative angle, the sine of negative theta, is the opposite of the sine of theta, right? Not equal like with cosine. Same thing for cosecant. Same thing for tangent. Same thing for cotangent. All the other four trig functions are odd. And you had these reciprocal identities as well. Right? Remember the secant of an angle was the reciprocal of the cosine, and vice versa. The cosecant of an angle was the reciprocal of the sine, and vice versa. And the cotangent of an angle was the reciprocal of the tangent, right? 1 over tangent, and the other way around too, right? Vice versa. You also had these quotient identities, right? Which just showed were developed showing you that the tangent and cotangent functions could be rewritten to be in terms of sine and cosine, right? The tangent of an angle is the sine divided by the cosine of that angle. And the cotangent is the cosine divided by sine. Remember, the tangent and cotangent are reciprocals, so if you just flip these over, you get the other one. And then one of the other set of basic identities you had to know, they're not going to be used here, but were these Pythagorean identities, right? So remember, the sine of an angle squared plus the cosine of that same angle squared would always be equal to 1. And if I take this equation here, this identity, if I divide everything by sine squared, you get 1 plus cotangent squared of theta equals cosecant squared of that angle theta. Then again, take that original one, sine squared plus cosine squared equals 1. This time divide everything by cosine squared, and you get tangent squared plus 1 equals secant squared. All right, so you got these three identities involving the squares of two different functions and the number 1 somehow, right? The squares of two functions and the number 1 in some way. All right, so noting all these again, all these identities, let's get to the expression at hand, and I'll write out the expression that was given to us in the problem. So we have the cosine of negative alpha, Right, the angle is called alpha instead of theta, no big deal. Multiplied by the tangent of alpha, multiplied by the cosecant of negative alpha, or the opposite of alpha, multiplied by the cotangent of the opposite of alpha. Alright, so I'm going to start off by using those even odd identities because I don't like having a minus sign in my angles, these negative alphas here. I'd rather have all of them just have alpha inside, like this tangent alpha. Get them all to have the same angle inside, the same expression inside. So, using the even odd identities, this is equal to, now the cosine of negative alpha would be equal to just the cosine of alpha. Right? Remember, cosine was one of the only two even functions. Times, then we have the tangent of, that already has just alpha in it. All right, now I'm replacing this here, so I'm going to put parentheses. The cosecant of negative alpha. Remember, cosecant is odd. Only cosine and secant are even. So the cosecant of negative alpha will be negative, or the opposite, of the cosecant of alpha. And the same thing for the cotangent. The cotangent is also odd. So the cotangent of negative alpha is the opposite of the cotangent of alpha. All right. Now, nice thing is I've got a negative 1 here times a negative 1 there. That'll make this all have a positive 1 in front. So I'm going to write that in the next line. So we have cosine alpha times tangent alpha, and then the two negatives when multiplied make positive 1. So now I'm just left with cosecant alpha, cotangent alpha. Okay. Now, the next step I'm going to do is just something I personally like doing. There's other ways around this. You don't have to do this. But I like to change every single function. I like to rewrite everything in terms of sine and cosine. And I suggest that to people because I find that for some reason people have an easier time dealing with things when they're sines and cosines and not other functions. So, using our basic identities, this one's already cosine, right? This is cosine alpha. The tangent of alpha, remember, is the sine of alpha divided by the cosine of alpha. The cosecant of alpha, if I want to write that in terms of sine and cosine, is, remember, that's 1 divided by the sine of alpha times, and then finally the cotangent of alpha is cosine divided by sine, right? Cosine alpha divided by sine of alpha. Now, you're just multiplying a bunch of fractions. So you would multiply the numerators, multiply the denominators, and then cancel any common factors. But perhaps you can see the common factors in the numerator and denominator right now, which I'm just going to do right now. So I've got cosine times sine times 1, which is really unimportant then, times cosine again. So I've got factors of cosine, sine, and cosine again in the numerator. And then I've got denominators of factors of 1. If there's no denominator, there's technically a denominator of 1. 1 times cosine times sine times sine. So I've got cosine, sine, and sine in the denominator. So the factors that the numerator and denominator share that I can cancel, there's a sine of alpha here in the numerator and a sine of alpha in the denominator. There's a cosine of alpha here in the numerator, a cosine of alpha here in the denominator. So those all become 1, the number 1. And that's it. All right, those are the only common factors I can see that I can cancel in the numerator and denominators. So then what am I left with? 1 times 1 times 1 times cosine alpha. Right, so I have cosine alpha left in the numerator. And then in the denominator, 1 times 1 times 1 times sine alpha. So I'm left with cosine alpha divided by, over sine alpha. Now this is perfectly fine, but there is a simpler way, a shorter way of writing this. Cosine alpha divided by sine alpha, remember one of those quotient identities, this is equivalent to cotangent alpha. And that's as simple as this can get. That's as little writing as I can do and still be equivalent to the original expression. So going back here, right, look at our choices, the cotangent alpha, the very last one there. And submit. Wonderful. Now let's see how they're doing it. I know they're going to do it differently. Yeah, see. Oh, no, they didn't change the last thing. See, they changed tangent, they did the even odd identities like I did. They changed tangent to sine over cosine. They changed cosecant to 1 over sine like I did. But then they left cotangent alpha as cotangent alpha because I guess they saw that you can cancel the sines, cancel the cosines, and you're left with just cotangent alpha. Again, there's multiple ways typically to simplify a trigonometric expression because there are so many of these identities that you have to know, right, and that you can use. Alright, so that's it for this second video. I think that'll be it. This is basically the kind of problem you're going to see with this objective. So hopefully this helps when you're working on this kind of a problem on your own. And thank you very much for watching.